Okay, so for this afternoon, I want to focus now down on this third spot on the diagram, which is pragmatic approaches and what they can do for the foundations of quantum theory. And so I'm going to look at a framework known as the resource theory framework. Right, so if you remember, I had this graph of a number of different frameworks, and down here, close to the pragmatic end of the spectrum, I had resource theory. So I want to tell you about what those are and how they can help us, axiomatize quantum theory in some operational approach, and maybe teach us something about the principles that will help us get a realist interpretation of quantum theory. So I'm going to tell you a little bit about how we came to be thinking about quantum theory through the lens of resource theories, and that's the story of entanglement theory. So there were people who, in retrospect, were thinking resource theoretically prior to entanglement theory, but I think this is the main avenue by which it sort of came into the foundations of quantum mechanics. So entanglement has been recognized for a long time. It was there in Einstein's argument. Schrödinger highlighted it. But it wasn't until the advent of quantum information theory in the 90s that people started studying entanglement as a resource. And it was really because of protocols like teleportation and dense coding that people realized that these entangled states could be used in these protocols to, for example, in teleportation, you use an entangled state together with a classical channel to simulate a quantum channel. And once that you've done that simulation, the entangled state has been used up. You can't use it again. And so it was natural to start thinking about entangled states as resources. If I want to have, n uses of a quantum channel, how much entanglement do I need? It became clear that if you had some pure entangled states that weren't maximally entangled, you could distill out some maximally entangled states from them. And it became very natural to start thinking about entanglement as a resource. And so people started asking, well, what should I allow for free? And it was realized that by allowing local quantum operations in Alice and Bob's lab, but only classical communication between them, you could never create entanglement, but you could manipulate entanglement. And there came a point where entanglement started becoming defined as the thing which is not free if what you have is local quantum operations and classical communication. And nowadays, I would say we're sort of living in that paradigm where sort of entanglement is most naturally thought of as the resource. Again, when you're working in a context where local quantum operations and classical communications are cheap and free and you don't have to worry about their cost, then entanglement is a resource, and that's effectively what entanglement is. So that pattern of identifying a set of operations that's free and then looking at everything that's not in that set and calling that a resource, you can repeat that pattern for other types of properties of quantum states and get other kinds of resource theories that are not about entanglement. So in entanglement theory, if you give me local quantum operations classical communication for free, then entangled states are a resource, non-separable states. But also operations, bipartite operations that are entangling, are also not free. So you can sort of pick out which quantum channels are resources. And you can think of all the things in this set and basically ask how they're related under processings that are free. The free stuff is what you allow an arbitrary quantity. Right? So you're allowed to use that stuff as much as you like. There's no limit on it. It all is free. And so you sort of want to understand what structure is induced here based on those free operations. So you might ask, can the entangled state phi be transformed to the entangled state psi using local operations and classical communication? You might try to work out, what are the deterministic interconversion relations among all the pure entangled states. That's part of the resource theory of entanglement, learning answers to questions like that. So here's two other examples of resource theories. You'll see a third example in David's talk. But what I like to call the resource theory of asymmetry is one where what's free are the symmetric operations. And I'm going to define precisely what that means in a moment. But in any case, it's sort of things that fail to break symmetry. Right? Those are free. And now anything that does break symmetry, so states that break the symmetry or operations that break the symmetry, those are resources. And now you can ask for two states that break the symmetry. Can I get from this one to this other one by symmetric operations? If so, they're ordered. And I can start working out the order in the resource theory. Similarly, I could take for free operations that are thermal at some temperature. And then anything, so you think of that as everything that's in thermal equilibrium at that temperature is free. anything that's outside thermal equilibrium, like a state or an operation, becomes a resource. And I also, again, I want to know the structure of the non-free things under manipulations that use only the free things. That's the pattern. These are the kinds of questions, sort of concrete technical questions, that you ask in resource theory. So one of the most basic ones is, what are the necessary and sufficient conditions under which one state that is a resource can be converted to another deterministically under the free operations? But you can also ask, not deterministically, but stochastically. You can say, what are the conditions under which psi can go to phi with some non-zero probability rather than with probability 1? All right, so in entanglement theory, the first question is answered by Nielsen's theorem for pure states. The second question was sorted out by Giffrey Vidal. And then there's another question, which is, can I do it catalytically? And that means, let's say I want to take psi to phi. Is there some other state chi such that psi tensor chi goes to phi tensor chi? So chi doesn't get consumed. It gets left over at the end. But maybe I can't do the conversion unless I have access to that other state chi. In that circumstance, we call chi a catalyst. And so it can happen that psi doesn't go to phi deterministically, but with a catalyst chi, it does go over deterministically, and the catalyst is left over. So that's another problem one can try to work out. People often look at rates of conversion. You know, if I have n copies of psi where n is arbitrarily large, and I turn it into m copies of phi, what's the rate m over n in the limit that n goes to infinity that I can achieve that conversion? So that's part of the asymptotic theory of the resource. A big question is, how can you define different measures of the resource? And I'm going to say a little bit more about what we should use, how we should define a measure of the resource. You might also ask for just necessary and sufficient conditions where, you know, some state can simulate some transformation in the resource theory. And then finally, you might have some operational tasks that you care about, like, you know, simulating a quantum channel. And then you might say, all right, well, what measure of the different measures quantifies the performance in some task? So if you give me a bipartite pure state, I might want to know its entropy of entanglement, because that tells me how well I can distill out maximally entangled states. So it tells me how well I can simulate uses of quantum channels with the state you've given me. The point is that all of these questions can be asked for any choice of those free operations, for the asymmetry resource theory, for the resource theory of athermality. In all those cases, you can, you know, try to answer these questions concretely. And if you ask, well, why bother? The answer is not because you have a burning desire to just know the answer to these questions. It's rather, I would say, that if you've kind of answered these technical questions, usually the sort of discipline that's required to do that means that at the end of it, you're much better able to characterize the limits of performance on the operational tasks that you care about. So, you know, we cared about teleportation and dense coding, but it wasn't until we had a sophisticated theory of entanglement that we really kind of understood what the limits were, right? And so the theory of entanglement really also just gives us a way of sort of understanding what's going on. It sort of synthesizes a lot of information, and it means that we now have a great facility. You know, somebody says, oh, I have this task I want to do. We're pretty, you know, we can say, oh, well, you'll need some entanglement for that, and here's how it works. We have good intuitions because we know all these technical results about how entanglement transforms. And the idea is that for all these other types of resource, that's true as well, that you might come to the table with certain intuitions about how that resource works, but once you've answered a lot of those questions, typically your intuitions shift, and you're like, oh, I wasn't thinking about this quite right. I now have a much better understanding of what this resource is and how to think about it, and now if I want to use it for something useful, I'm better able to do that. That's the first reason. So ultimately, that's about, you know, some pragmatic aims I have, like using a quantum channel, simulating a quantum channel, or something like that. And I want to understand what my theory, like say quantum theory, tells me about how well I can do that. So, you know, quantum theory says everything there is to know about entanglement, but it wasn't until we had the resource theory framework and we'd answered these questions and learned that the mathematical theory of majorization, for instance, is pertinent to the conditions under which you can deterministically convert. Only then could we really sort of answer the questions we cared about based on the truth of the formalism of quantum theory. So this is the sense in which there's sort of a lot of technical work to be done to make the connection between the well-defined theory and what it means for what we can do in the way of, you know, certain kinds of pragmatic goals. But there's a second reason, a more foundational reason for why you should do this, which is that in my experience, once you've solved all these technical problems, usually it leads to a lot of kind of conceptual innovation. It leads you to think about the property you're studying, the thing which you're characterizing as a resource in a new way, in a more subtle, refined way than you did before. So I want to try to explain what I mean by that. So roughly speaking, it's, has the promise that maybe it can help us understand what the correct realist interpretation of quantum theory is by better understanding sort of the capabilities of manipulating some resource that will allow me to think about that resource in a more conceptually accurate way. Like, what does it really mean? So in the toy theory, we saw all these mathematical features of quantum theory get a certain meaning in terms of states of knowledge and how states of knowledge can be teleported and steered and not cloned and things like that. And it's a similar idea here, that things like entanglement and asymmetry and athermality, deviation from thermal equilibrium. There's also a question of what's the best way of thinking about those things? In the last lecture, there was this idea that, a lot of the features of entanglement and we can actually make sense of by thinking of it as simply statistical correlation in a classical theory with certain features. If I have that take on entanglement theory, now I can reason better about it and figure out maybe what I can expect to do with entangled states. Okay, so let me give you a bit of preliminaries about how resource theories work in general, and then I'm going to talk about the resource theory of asymmetry specifically. So some of the next slides will also be background for some of what David will be talking about in his lectures. So a process theory, and here it's going to be general enough that we don't even need to be talking about quantum theory. This could be a GPT, for example, a generalized probabilistic theory. So I'm going to characterize it as a process theory. So there's going to be different types of systems, A, B, C, etc., including a trivial system, which I'll represent as no wire. So you can think of this as a trivial input and a non-trivial output, for example. And then you got different processes, which I write by lowercase letters. And some of those processes have inputs and outputs. Some have multiple inputs, multiple outputs. Some have no inputs. These are states, bipartite state, unipartite state, and so forth. And we want to imagine that this forms a theory in the sense that if you give me things, processes that exist in theory, and I wire them together, matching the types of those wires, I'll get another process that exists in the theory. Okay? So it's closed in that sense. And now the key aspect of a resource theory is that you find a sub-process theory, a subset of all these processes, which you declare to be free, which means you're allowed to avail yourself of those in any quantity you like. And the rest are non-free. All right, so now you again have to demand that any wiring together of the free stuff is closed. That no matter how I wire them together, I get something else that's already included in the free set. I can't leave the free set by just wiring together free things. That's the constraint, because otherwise, you would basically be saying things that are expensive can be built from things that are free, and then the theory collapses. It doesn't make sense. But you can typically find a lot of interesting sub-theories of the process theory that are non-trivial, right? A set of things that I can wire together in arbitrary ways that's still free. And an example would be things I can do with local operations classical communication is a strict subset of all the things I can do. It's closed, and it defines a partition between what's free and non-free that's non-trivial. And so it defines a non-trivial resource theory. So that's the definition from this paper of mine, that a resource theory is a partition process theory. There's the full theory of all the processes, there's the sub-theory of the free processes, and it's the partition that this defines in your theory that ultimately characterizes what resource theory you're talking about. Okay, so then, questions like state conversion become, can I take, say, a state R on A to a state S on B for free? That's just asking the question of, is there some process which has A as input, B as output, and is in the free set? If so, then I say this conversion is possible under the free operations. If not, it isn't. I can do that for channels as well. Can this free channel go to this free channel? Well, what is the type of processing that will take a channel to a channel? Answer, it's a pre-processing with the possibility of a side channel. Here, the input C has to match the target input. The outputs have to be the input to F and the side thing, and then a final processing back to D. So if I can find a set of free operations that allow me to do this, then F goes to G by free operations. Finally, you don't have to be state to state or process to process. You could also ask, can some non-free state be transformed under the free operations to some non-free channel? And then I just have to go find the right type of processing that will achieve that and ask whether there exists anything in the free set that'll do it. Okay, so oops, what am I doing? I could obviously do lots of other examples of this. These are just meant to be representative. So suppose you work hard and you find for a bunch of resources, R1, R2, R3, R4, you start to figure out which of these pairs of resources there exists a free operation that takes you from one to the other. So you find that there's a free operation that takes R1 to R2. There's no operation that takes R2 to R3 or R3 to R2, so they're incomparable. R2 goes to R4, R4 goes to R5. Note that R1 clearly has to go to R4 because I could convert it to R2, and then R2 can be converted to R4. So this diagram is meant to be sort of closed transitively. R3 prime here is something where I can convert R3 to R3 prime, and I can also convert R3 prime back to R3 using the free operations. So at the end of the day, what you get is what's called a pre-order. And this is just a very simple example. It's often nice to find equivalence classes. So R3 and R3 prime, from the perspective of their resourcefulness, are the same thing, right? Because I can go back and forth between them. So if all I care about is doing some tasks that require this resource, it doesn't matter whether you give me R3 or R3 prime, because the free operations are things I can do in any quantity I like, so I can convert between R3 and R3 prime. I don't care. So it makes sense that I would just lump them together into an equivalence class. And so what we often do is we quotient the whole set of resources with respect to the equivalence relation of being, the same under the free operations. And what we really want to characterize is the partial order of the resources. So in entanglement theory, all we really care about for a bipartite pure entangled state is the Schmidt coefficients, because the local basis of Hilbert space is something I can change by a local unitary, and that is already part of the free operations. Local unitaries are free. And so I don't care whether it's this entangled state or that entangled state. If they have the same Schmidt coefficients, they're equivalent as an entangled resource. So that would be one example of what quotienting with respect to equivalence looks like. Okay, once you've characterized your resource theory as a partial order, different types of resources might be different partial orders. So, the mathematical theory of called order theory is not something as physicists we tend to study, but there are kind of different notions of partial order. So you could ask, one basic one is your partially ordered set totally ordered, meaning that there are no incomparable elements? So unlike the example I had here, maybe it's just a big chain, right? And there's no pair of systems that are like this. Basically, for every pair of systems, one is going to be above the order in the partial order. In that case, we say it's totally ordered. So you might ask, is my resource totally ordered or not? In entanglement theory, if I talk about asymptotic convertibility, it's just this one measure, the entropy of entanglement, that determines sort of where I am, how good my state is, a pure bipartite state, how good it is in terms of the rate at which I can distill EPR pairs, and so it is a total order from that perspective. But if I'm looking at single shot, then it's not a total order, okay? And in general, I would say you rarely have a total order. There's a question of whether the incomparability relation is transitive or not. The height of the order would be what's the length of the longest chain. So a chain is like a set of elements that have arrows between them. An anti-chain is a bunch of things that are incomparable, so I might want to characterize the height or width of my partial order. Anyways, there's a bunch of properties you can look at that distinguish different types of partial orders. And that tells you something about the nature of your resource. All right, measures of a resource. So the most general approach, and this was sort of learned in entanglement theory the hard way, where people typically added a lot more conditions on what a measure of entanglement should be. But finally, they realized that, look, the only condition you should ask for a measure of resources is it's a function from resources to the reals such that if R1 can go to R2 by the free operations, then M of R1 has to be greater than or equal to M of R2. So this is a function that should be non-increasing as I move down the partial order. So if I take a step down the partial order, so I move from R1 to R2 for free, then maybe the measure hasn't changed, but it's not going to increase. Okay, so in a diagram, that means that this function just has to be an order-preserving function. So in this simple example I gave, if I wrote a function that takes one value in this region, a different value in this region, a different value here, here, and here, so like here I'm sort of dividing up the different sets of values of that function m1, well, this is order-preserving because there's never a case where one resource is below another and gets a higher value of m1. Okay, so here R2 and R3 are incomparable. R2 can have a higher value of M1 than R3 does, but that's okay because R3 cannot go to R2, so it doesn't violate this condition, right? So basically I'm allowed to do that. And note that when you have incomparable elements, it means that there's another monotone that assigns a higher value to R3 than to R2, and that's fine as well. And this is characteristic of something that isn't totally ordered. If you're not totally ordered, then there will be more than one monotone that's order preserving, even though it's maximally fine-grained. And this is a simple example where there's two such monotones. So the lesson here is that if your resource theory is not a total order, then there cannot be one measure to rule them all. And this is sort of a warning, because in a lot of the entanglement theory literature, in the early days especially, there was this idea that, hey guys, I have a new entanglement measure, and it's really good, better than all the other ones. It's the one. This is the one you should all be thinking with. But if you think in terms of order theory, there is no single measure that actually characterizes the partially ordered set of resources. And that's all the information that there is to know, is the partial order. Okay? And so if it's not a totally ordered set, one monotone will never do the job. What can do the job, however, is a set of monotones that are complete in this sense. So I say a family of monotones is complete if it completely characterizes the pre-order or the partial order, which means that whenever R1 goes to R2, that's true if and only if, for the set of these monotones, R1 has larger values for all the monotones than R2 does. So if I can find a single monotone where R2 has a larger value of that monotone than R1 does, then that tells me they can't be ordered. And if you give me such a set of monotones, I can recreate the partial order, right? I can draw out exactly what the connections are based on the values of all those monotones. Okay, so that means that in entanglement theory or any other theory, if you really want to know the ground truth, which is the partial order, that's all there is to be known ultimately in the resource theory, then you should be looking not for a particular monotone, but a complete set of monotones. There might be many complete sets of monotones, but what you really want is a complete set. And so if we talk about deterministic conversion of bipartite pure entangled states, we do know how to write down a complete set of monotones for those guys. That's in some work by Guy Vidal again. Okay, yes? Mike, yes?
Sorry, maybe it's just a formality, but what prevents me here from choosing all the monotones to be exactly the same guy? I get a complete set, right?
Well, if all the MIs were the same, then it would not be true that checking that this held for all the MIs would imply this, right? It would be missing information. So the condition that these inequalities has to imply that forces this set of monotones to be non-trivial in the case where it's not totally ordered. If it's totally ordered, then it's fine. But you're right that, you might want to say something like, oh, give me a minimal complete set in the sense that there's no redundancy, and maybe the third monotone isn't just a linear combination of the first two monotones, it really says something new. So, strictly speaking, you could ask for more than completeness. You could ask for a kind of minimal type of completeness.
Thank you.
Yeah. Okay, so I want to tell you now about the details of this resource theory of asymmetry, and give you some idea for what it can teach you about asymmetry. So first of all, pragmatically, why do we care about the resource theory of asymmetry? Well, it turns out there's a lot of important tasks like clock synchronization, aligning Cartesian frames, which are maybe represented by some gyroscopes you have, or the global positioning system, which can all be thought of as ultimately about symmetry breaking. So what is a clock? It's something that breaks time translation symmetry. And the quality of a clock has something to do with sort of how much information about time I can estimate from the state of that system. Similarly with Cartesian frames, those are breaking rotational symmetry. And so a state that breaks rotational symmetry is a candidate for something I could use in my lab to figure out, how I'm oriented relative to the fixed stars. And if I want to communicate to you information about a direction in space, I need to send you something that isn't rotationally symmetric. It has to be rotationally asymmetric. And with the global positioning system, what you really want is to be breaking spatial translation symmetry. So if you have systems that break spatial translation symmetry, they can be used to locate an object. And the more asymmetric they are, the better they are, the more precise location you have. So in the context of the resource theory of quantum asymmetry, people have studied the applications to all these kinds of tasks. So that's sort of the pragmatic angle on why you would want to study this. This is sort of the natural setting for a resource theory. It's because I want to solve these sorts of problems that I'm studying the resource theory. That's the natural motivation. But I'm going to also try to give you the foundational motivation by giving you a conceptual puzzle. So it's often useful to set up a conceptual problem when you have something that looks like a good principle, and then you see something that's an apparent counterexample. So here's something that looks like a good principle. It was suggested by Pierre Curie, and so it's called Curie's principle, and it says this: any asymmetry in a physical effect must be found in its cause. So maybe you've never heard of Curie's principle, but I'm pretty sure that you use this in the following sense, that if you're solving a problem in physics, and you get an answer, and you notice that the answer breaks some symmetry, and then you look at the statement of the problem, and the initial condition didn't break the symmetry, and the dynamics didn't break the symmetry, but your solution breaks the symmetry, suddenly you realize, oh, I've made a mistake. This doesn't make any sense. Where could that broken symmetry have come from if it wasn't there in the statement of the problem? So that's exactly the intuition behind Curie's principle. He was studying it in the context of crystallography and the interaction of matter with electromagnetic radiation, but it's basically the intuition that you already have, that sort of symmetry breaking, wherever it is found, sort of needs an explanation. And I'm going to be interested in not just that, but a quantitative version of Curie's principle, which would be if you now have a quantitative measure of asymmetry, you might think that the measure of asymmetry in a physical effect cannot be greater than the measure of asymmetry in its cause. So it's not just is the symmetry there or not, but you might think that if your solution has a higher measure of asymmetry than the initial condition, then you have a problem as well. Okay, so on the face of it, this seems like a reasonable principle. So what could possibly be wrong with it? Well, imagine this. So you have a rod, you have a cylindrical rod, solid, and you press on it till it buckles. And then you notice that it buckles in one particular direction. Out of all the 2 pi directions it could have buckled in, it chooses one, and it buckles. So, show of hands, who thinks that this is a violation of Curie's principle? And now, who thinks it's not a violation of Curie's principle, but it is a violation of the quantitative Curie's principle? No. Okay, good. So hold on to that. Here's a second example. Suppose, this is a quantum example now, suppose I set up a particle in an S-wave wave function, and I have a spherical detector around it. Okay, so I let it propagate, and then the particle gets detected, and we'll imagine it's a non-demolition measurement. So it survives that detection and propagates outwards, but now it's become localized. And quantum theory predicts that I'm going to find some detection, uniform likelihood to find it anywhere, and then after that it heads off as a localized wave packet. And so now the question is, for a particular outcome of this measurement, where we've gone from something that does not break rotational symmetry to something that now picks out a direction in space, is this a violation of Curie's principle? Who thinks yes? Okay, and does anyone think that it isn't a violation of Curie's principle, but it is a violation of the quantitative Curie's principle? Okay, so I want to try to persuade you that by thinking about the resource theory of asymmetry, it suggests a way of maybe salvaging Curie's principle, or how to think about Curie's principle given these examples, given this apparent contradiction of the principle. So I'm going to define the resource theory, tell you about some results, and then we'll come back to those puzzles at the end. So, okay, what do I mean by the free operations in this resource theory? They're the ones that are going to be symmetric. So what do I mean by symmetric? So first of all, there's lots of different symmetries I could consider, right? So we already saw it could be rotational symmetry I care about, time translation symmetry, spatial translation, all those different applications had different symmetries. But you can really do this for any symmetry. So just imagine you have some group G and a unitary representation of that group. So this might be physical rotations in space, or it might be translations or whatever you like. And so now suppose you give me an operation. So by that I mean a completely positive trace preserving map. I'm going to say it's symmetric if it commutes with the action of the group. So meaning if I take a state and I perform the symmetry operation on it and then I apply this channel, or if I first apply the channel and then perform the symmetry operation, I get the same result for all states. So in a diagram it looks like this. The channel E commutes with the superoperator action of that group. So if I think of that as a group action on the operator space. So this has to be true for all elements of the group. Here's an example. If I have a spin 1/2 system, right, so a little spin that can point in any direction, so it's described by the Bloch sphere, and I consider the channel that depolarizes the Bloch sphere symmetrically. So it takes states on the surface of the Bloch sphere and pulls them towards the origin by some amount. Well, if I do that operation and then rotate, or if I rotate and then do that operation, I get the same thing. Okay, so the depolarizing channel is rotationally symmetric because it commutes with all the rotations. Okay, so this is how I'm going to define the symmetric operations for a group. They're the ones that commute with the action of the group. So if you ask, well, what is a measure of asymmetry for this group? It's any function A from the states to the real such that if rho goes to sigma under symmetric operations, so operations that commute with the action of the group, then A of rho should be greater than or equal to A of sigma. So then you want to know, how do you find measures of asymmetry? And now, I should say, before I get into this, I mean, I could tell you many more details about this resource theory. I could tell you a long story about the conditions for deterministic conversion, and there's a story about Noether's theorem, and there's all this interesting stuff. But we don't have time, so I'm going to just tell you a little bit about measures of asymmetry so that we can get back to our motivating example. And then near the end, we'll talk a little bit more about philosophy. So I'm going to focus in on finding measures of asymmetry. And then there's this question of, how do we find them? I suppose you could have a guess, and then you could try to prove mathematically that it has the property of being non-increasing under these symmetric operations. That's a way to go. But this is where sort of physical insight comes in, that by thinking about asymmetry in a more conceptual way, so I started thinking about this stuff because I was working on quantum reference frames. And reference frames are really about you need a reference frame to talk about a symmetry operation. So by virtue of thinking about reference frames, my student Iman Marvian and I were able to see that there's an interesting connection between the problem we're interested in here, which you could think of as a problem of constrained dynamics, like you want to convert rho to sigma via some constrained set of maps, the ones that are symmetric. There's a corresponding problem just in pure quantum information theory, where there's no symmetry constraint at all, which is one where people spent a lot more time thinking, right? Because quantum information theory is now well developed. So the idea is this, so just look at the equations for now. Rho will go to sigma by the symmetric operations if and only if the orbit of rho, so take rho and find all the images of rho under every element of the group. I want to call that the orbit of rho. So if I had like a spin-a-half particle pointing in some direction, and I apply all possible rotations to it, I end up getting images of rho under all those rotations. That's the orbit of that state under the group. So this is true if and only if the orbit of rho under the group goes over to the orbit of sigma, in the sense that a particular element in the orbit, the gth element in this orbit, can go over to the corresponding element of the orbit of sigma by some single operation. So this operation E, one and the same operation, has to take every element of this orbit to the corresponding element of that orbit. Okay, so that's what this diagram represents. Some element of the orbit of rho, you act E on it, and it goes to the corresponding element of the orbit of sigma. Now, if you forget for a moment that the elements in this set are labeled by a group, all this is saying is that this set of states goes over to this set of states under some processing. And that's a problem in information theory. I might say, okay, I have a set, it's encoding some classical information. Let's say the set has n elements in it. So it's, log n bits of classical information is encoded in this set. I have a message 1 to n. I prepare a quantum state, row I, to encode that message. Question, if I'd encode the message in the states sigma I, a different set of states, is it possible that by sort of adding noise to the first set, I could have gotten to the second set? If so, then this second set is less informative than this set. It does a worse job of encoding that classical information, right? And I would say that they're ordered. This one is strictly worse at encoding that classical information than this one is, because there's some process that'll take me from this encoding to that encoding. If there's a process that takes me from this encoding to that encoding, and another process that takes me back, I would say, oh, they're equivalently good at encoding this classical information. But the point is that asking questions like, is this set of state, does it go over to this set of states under any operation at all? That's just what we usually ask in quantum information theory. That's about the capacity of sets of states to encode classical information. And so we do have a theory of, what's a measure of information in this context? Okay, so we can now leverage the theory of how to measure information in this context to get measures of information in that context. All right, so if you give me something that measures how much information about the group, so here the classical message is a label of the group. So what I'm really doing is I have this classical information, which is an element of the group. I encode it in a quantum state by just rotating the state to the by the corresponding group element, and that's the thing for which I'm trying to measure the informativeness of that encoding of the group. And so I can use any of a bunch of standard ways of measuring information. So here's, if you want to know why is this if and only if true, this is where the intuitions about reference frames come in. The reason, I could give you a simple mathematical proof. It's not hard to see that it's true just with some algebra. But here's the intuition behind it, which is that these two problems here, rho goes to sigma under symmetric operations, and this one, are just two perspectives on the same problem. So imagine you have Alice and Bob, and they don't share a reference frame, which means there is some relationship between their local frames, but they don't know what it is. So they just assign a uniform prior over all the possible group elements that could relate their two reference frames. So now suppose they're trying to do this task. Alice sends a system in state rho over to Bob. Bob does some operation on it, sends it back to Alice, and the question is, can she get sigma back? So if you think about this from Alice's perspective, or relative to Alice's frame, she's sending out rho, she needs to get sigma back, and now there's a constraint on what Bob's processing could possibly do, because Bob's doing something specific relative to his frame, but she doesn't know how that frame's oriented, so she averages over all the possible relative orientations, and so she adds this noise to what he's doing. She's like, it's not any old operation he's doing. She does a symmetrization over the whole group, and that makes the effective operation one of these symmetric ones, one of the ones that commutes with the group. So if you work out what are the sum total of things that could be done over here, the answer comes back, it's just the things that are symmetric, the things that commute with the group. So from Alice's perspective, we're on the left-hand side. We're just asking, is there any symmetric operation that can achieve this rho to sigma conversion? But if Bob describes the very same protocol, he now says there's no ambiguity as to what's being done. It's definitely E relative to this frame, right? But now there's ambiguity as to which state he's getting. He might be getting rho. He might be getting some rotated version of rho. It all depends on how Alice's frame is related to his. So for every group element that could describe the relation of Alice's frame to his, there's a different possibility for what she's sending him. And so he thinks of it, I'm getting some element of a set of possible states from Alice, right? And that's just this set here, right? The orbit of rho. And he describes the problem as, I have to send back the corresponding element of the orbit of sigma. That's my job. And I have one transformation to do it. So that's exactly what we saw over on the right-hand side. Okay, so this is how we came to it. It was by thinking about reference frames. We saw that these things were equivalent, and we saw that, results about information theory have already answered the kinds of questions we care about, which is coming up with measures of asymmetry. It's useful to also think about a classical analog of this, which is, if instead of quantum states I have probability distributions over a sphere, then intuitively I might think that this probability distribution has more asymmetry than this one, They're both clearly not rotationally symmetric. Only the uniform distribution over the sphere is rotationally symmetric. So you might think that's more asymmetric than that. But what that really means is that if you take the orbit of this distribution under all rotations, the amount of distinguishability of the original guy from its rotated version is higher here than it is here. These guys overlap more than they do here, so I have more distinguishability. So the asymmetry is really quantifying something about how much information about the group element can be encoded in a particular orbit. This, if I build my orbit on this distribution, I can encode more information about the rotation than if I build the orbit out of this distribution. So it's the same thing with the quantum states, but with the distributions, I think it might be a little bit easier to visualize. Okay. So as I said, any measure of the amount of information about the group encoded here is a measure of asymmetry. So you can just take all your favorite measures. So some of you may not be familiar with quantum information theory, but I'm just going to say that there's something called the Holevo measure of the amount of information in a set of states for encoding classical information. And if you take that measure, then what you get is this measure of asymmetry. So here, now let me just sort of show you what it means. It says, take your rho, take any distribution over the group you like. You could take the uniform distribution, and do this operation here, which we call twirling, right? So you're averaging over the group now. And compute the entropy of that guy, and then subtract off the entropy of rho. So if you think about that, say we have our spin half example. I start with a pure state rho. It has entropy 0. If I took that pure state and I averaged it over the whole group, what would I get? I would get the completely mixed state. It has 1 bit of entropy now. And so this difference would be large, right? 1 bit. It has the maximum asymmetry it can have. If I instead it started with a rho that was already halfway towards the origin in the block ball, it already has some entropy, and I twirl it, well, that difference is going to be smaller because now this original state had some entropy to begin with. And so clearly the difference is sort of tracking how much that state is breaking symmetry, how distinguishable are the different elements of the orbit of that state. So it sort of just passes the intuitive check that, states that I intuitively say are highly asymmetric get a high value, states that have a low measure get a low value. You can use other measures of information to get other measures of asymmetry. So you might intuitively think, so if L is a Hermitian operator that generates the transformations under the group. So if we're talking about rotations, this could be like the angular momentum operator along some axis. So non-commutation of your state with that generator indicates that the state has some asymmetry, because if it were invariant under the group, then it means that if I acted on both sides of the state with e to the I L times some parameter, it would do nothing. L would have to commute with rho. So you can look at the measure of this non-commutativity, and you can prove that that's indeed another measure of asymmetry. And then there's this funny one called the Wigner-Yanasi-Dyson skew information, where for every value of S, you look at something. This looks a little bit like the variance of L. Like if rho was pure and S was equal to, let's see, if S was equal to 1, if S was equal to a half, I think this just becomes the regular variance for a pure state. That's right. But it's a generalization of the variance. Anyways, this also is a measure of asymmetry. And I mean, they're not trivial to write down. But now you just have a kind of crank that you can turn. You can take every measure of information, turn it into a measure of asymmetry. So let me first point out that this pragmatic angle, which is like, oh, we have all these tasks like clock synchronization, frame alignment. Those are called tasks in metrology, right? When you're trying to come up with standards for lengths and time and things like that, and orientation. These are all called metrologic tasks. And so a typical metrologic task would be something like estimating, say, the strength of a magnetic field, right? So that's an example of metrology. I want to build a probe for how strong this magnetic field is. So I send in a spin, the spin precesses around the magnetic field, and then I try to estimate how much did it rotate, because that's a proxy to the strength of the magnetic field. And so people often, there's statistical fluctuations in your estimate of the amount of phase that it's picked up. And you can show that the thing that you usually use to sort of see, how much phase it's acquired, which is the variance in this unbiased estimator, You can bound it by what is a measure of asymmetry, right? So this is just that formula I showed you on the bottom for the case where S is equal to half. So sure enough, the intuition that it is the amount of asymmetry of your state of the spin that determines how well it can estimate phase. If it was totally symmetric, then you wouldn't be able to detect any rotation at all. But if it's highly asymmetric, you're better able to detect the rotation. And that's reflected in the fact that you can derive a bound which is a measure of the asymmetry of that state. And so that's kind of the big picture here is that if you're thinking about metrology and you care about how well you want to do these metrologic tasks, you shouldn't be using entanglement theory. So there's if you read the papers, people will often say, oh, entanglement must be the resource. Why? Because entanglement's always the resource. No, here, asymmetry is the resource you should care about. And so any differences of states, that just keep me in the same equivalence class, they're irrelevant. It's how much asymmetry does it have? Where does it fall in the partial order of all states under the symmetric operation? That's what's pertinent to its performance. And so you should be using the resource theory of asymmetry to do metrology. All right, so conceptually, what does this bridge lemma that I told you about mean? In terms of the partial order that's defined by the resource theory, over here in the resource theory of asymmetry, I had a bunch of states and they're ordered by symmetric operations. Over here, I had elements which are now orbits of states, right? So sets of states in every place. And they're ordered not by symmetric operations, but just data processing, any operation at all. And there's essentially an isomorphism between those two orders. That's what the bridge lemma showed. So when I say that there's no increase of asymmetry under symmetric processing, that's the same thing as saying there's no increase in the measure of information under any data processing whatever, which means that the quantitative Curie's principle, which I told you about earlier, just follows from the principle that you can't increase the measure of information just by data processing. And that principle is really obvious, right? Like when you learn it in information theory, if I have some set of distributions that have a certain amount of distinguishability, and then I feed them into a channel, I don't expect what comes out the other side to be more distinguishable. Like if I lose the information by adding noise, it's gone. There's nothing to be done, right? Processing can only increase the amount of overlap that these distributions have. It can't decrease it. So the intuition that by processing something, adding noise, or just permuting it, you're never going to increase the amount of distinguishability of a set of distributions. That's what ultimately fuels the quantitative Curie's principle. So you should believe this. Why? Because this is very obvious and clearly correct. Okay, yes?
In metrology, to talk about distinguishability, isn't it considered optimal to use quantum Fisher information?
Can you repeat the question?
The question is, isn't it optimal to use quantum Fisher information to characterize the performance? Yeah. I mean, I think the quantum Fisher information is a good choice. It's not the only choice for characterizing the performance of a metrologic task. But yes, you can look at the quantum Fisher information, and what you can show is that you can find upper bounds on the quantum Fisher information that are indeed measures of asymmetry. So some of the best bounds we have on that quantity can also be proven to be measures of asymmetry. Yeah. Yes.
Are there situations where we could use either entanglement or asymmetry or both, or how does it work?
Yeah, what's the connection with entanglement theory? So I've argued that entanglement is not the resource that powers metrology, it's asymmetry. But it does happen that sometimes two different notions of resourcefulness are tied together. So it can happen, for example, like if I consider 3 spin-1/2 particles, and I say, please go find me the states of 3 spin-1/2 particles that are maximally asymmetric relative to this measure that I care about. So then you go and you search among all the states to find the one that's maximally asymmetric. Generically, you'll find that those maximally asymmetric states are entangled, that you can't achieve the maximum value of that using product states. So that's a sense in which, to get the maximal asymmetry, I need the entanglement. But if you give me 2 spin-1/2 particles, actually I can achieve the maximal amount of asymmetry with just product states, right? So it's not as if I need necessarily always to have entanglement, but sometimes they go together, that having asymmetry of a certain type might require entanglement. But if you just went and tried to maximize entanglement, you would be maximizing the wrong thing, right? Because that's not optimized to the task you care about. Yes?
I had a question about the quantitative Curie principle.
Mm-hmm.
kind of in conflict with like this intuitive notion we have like the butterfly effect or chaos theory in general, like small asymmetry seems to generate a very large amount of asymmetry in the end when you like wait long enough and let it go through processes.
Okay, hold on to that thought because we're about to get there. Any more questions about this? Because now I'm going to get back to those thought experiments from the beginning. Okay. Yes.
And I'll just maybe it's very simple. Whatever you have explained, it works in the same way with I don't know a discrete group. If you have a
Yes.
discrete group, it's the same.
It is, yes. You can do this with discrete groups. In fact, there are some interesting differences between discrete groups and finite groups, which is that with a continuous and discrete. Like with a discrete group, if I have a finite dimensional Hilbert space, I could still find a set of states that are orthogonal to one another and form an orbit of the group. Whereas if I have, say, the rotation group, and I have a finite dimensional Hilbert space, I will never have a perfect encoding in the group because I don't have infinite dimensions, so I can't make all the elements of the orbit orthogonal. So often with continuous groups, as long as your resources are fixed, you don't have arbitrary energy or something to work with, you always have an imperfect encoding of the group. So that's one interesting difference that comes up in this. Yeah. Yep.
I don't understand why essentially we should talk about asymmetry, because I feel like it's more about distinguishability than asymmetry, but maybe the argument is that they are related, and okay, but
yeah.
I feel like there's no need for symmetry except for the fact that we are using a group.
So the notion of distinguishability is broader in the sense that I could write down sets of states and ask how will they encode a classical message chosen from one set of possibilities without those sets of states being orbits of some group, right? So in a way,
yeah.
The resource theory of asymmetry is about how well a given state can encode a very particular type of classical message, namely a classical message that picks out an element of a group and has that group structure. So the set of states is required to be the orbit under the group of a single state. And so it's sort of about the distinguishability or the information encoding capacities of those kinds of sets of states that ultimately determines how much symmetry breaking a given state has in this sense over here. So, the intuitions we used here is that asymmetry is the thing that you cannot create for free. What does free mean? Free means just using an operation that's symmetric that I don't need a reference frame for. Right? Like I have no reference frame for orientation. I can still do depolarization. I didn't need to know which way was up. All these things that commute with the action of the group are things I can do without any access to a reference frame that breaks the symmetry. So they're the things that I don't need to break the symmetry to do. So that was the intuition. And then to kind of rank the different types of asymmetry, I just say, oh, let me figure out the partial order. Under the free stuff that I don't need any asymmetry to do, how are they ordered? That's my notion of asymmetry I start with. And then I learn through this sort of analysis that that's exactly the same as how much information does this state encode about the group. So it's this connection between information theory and symmetry breaking. Okay, so let's get back to this puzzle here. So we had this column that buckled, and so we could say, what does our resource theory of asymmetry say about this? So I could take a measure of asymmetry and say how much measure did the initial column have. And now we know a measure of asymmetry is just how well is it encoding information about the group. In this case, we'll just talk about the group of rotations around the circle perpendicular to that axis. And what we normally think of as that this thing will buckle presumably because there's a microscopic defect somewhere in the column. So it already had a bit of asymmetry, namely there was like some atom that was dislocated, and that broke the symmetry, right? So there was like a single atom's width of resolution. So if I could go in, see its quantum state, and say, right, it picks out a direction in space, to resolution of one atom. that's the quantum state. This is how much asymmetry it has. After it's buckled, the resolution is still only 1 atom wide. I mean, now it has a macroscopic buckling, but it's still, there's like an atom that's building up the whole thing. So at the end of the day, I'm still not going to resolve a direction space better than 1 atom's width. So the measure of information hasn't increased. This thing was already able to pick out a direction space, 1 atom wide by virtue of that defect, and this can do no better. So the amount of asymmetry, though, sort of from our macroscopic point of view, it looks like it, we can learn more. Fundamentally, we can't. The quantum state initially had just as much information about orientation as the final state did. Good. And then let me tell you one other result from the resource theory of asymmetry to get back to our S-wave propagation case. There's something in the resource theory of asymmetry that goes by the name of degradation of quantum reference frames or degradation of asymmetric states. And it's the idea that if system A here is in some asymmetric state and I use it, so maybe it's a reference frame for orientation in space and I want to use it to figure out how some other system S is oriented. So I bring them together, I do some processing of the two, maybe a measurement where I try to learn how this guy's oriented with respect to that guy to estimate, like this might be like a baby reference frame. It's my sample of your reference frame and I want to know how this system S is oriented relative to your reference frame, so I measure. Every time I do that, you can prove that I degrade this reference frame a little bit. I make it less asymmetric by virtue of that interaction. This is for the case of continuous groups. And so you can't really use a reference frame, for some pragmatic purposes unless you let it suffer some degradation. So rho A prime, which is the final state of A when you trace out the system, is generally a little bit less asymmetric than rho A is. And that's something that comes out of just sort of working out how this resource theory works. And there's a number of papers that study, for example, how quickly that degradation occurs as you increase the number of measurements you use this state for. This is an example from quantum optics. Now the point is, what does this mean for our puzzle here? If this can certainly look like you got asymmetry from nothing, but when you think, this old trick that we always do in quantum information, let's think about this thing that we're calling apparatus as a quantum system. Let's try that. So the detector, we were thinking of it as this external thing, but let's think of it as a quantum system itself. Did it have asymmetry to begin with? Well, it must have. If it didn't, I couldn't have used it as a detector. I couldn't have used it to say, here's where I found the particle. Relative to my lab, it's got to have some marks on it that say, here's, this is sort of the origin of my Sterdian coordinate system. So clearly, it had asymmetry to begin with. And the results from degradation of reference frame tells me that by virtue of interacting with the system and trying to measure how this guy is oriented with respect to the lab, its asymmetry will be degraded. So, yes, the particle has gone from having no asymmetry to some asymmetry at the end, but the asymmetry of my reference frame has gone down. So the quantitative measure of asymmetry hasn't increased in total. The particle might have gotten some asymmetry, but it's more than compensated by the fact that the detector has lost some of its asymmetry. And if you don't take into account the detector, you might not notice that, and you might think, there's a violation of quantitative Curie's principle here, but that's not the case. And if you look at any of these quantitative measures of asymmetry, and you notice that the interaction between the particle and the detector is totally symmetric, you can prove that for any measure of asymmetry you care about, the final total system of apparatus and particle does not have more asymmetry than the initial system had by any measure of asymmetry. So the quantitative Curie's principle is satisfied. Okay, yes, there's a question.
Hi, yeah. So I don't really get, why did the detector's asymmetry decrease?
Well, I haven't really taken you through the proof of that, but so I'm asking you to trust me that when you do the math and you ask generically if I have any system that's acting as a reference frame and I interact it with another system to try to measure the relative orientation between them, the formalism of quantum theory just implies that the asymmetry of that goes down. So can you understand that from an information theoretic perspective? There should be, like across this bridge I talked about, there'll be a counterpart to that fact. So let me just think for a moment what that would be. Yeah, I guess it's like this. Like if somebody is sending me a message and the message is a group element, like a direction in space. So how do they encode that message? They encode it in this particle and this apparatus. It's a weird way of encoding a message, but that's how they do it. They send it to you, okay? Particle, it's in an S wave. Apparatus, it's asymmetric. And along the way, the particle evolves and it gets what we call detected by the apparatus. Think of all that as just a big unitary evolution on the system I've sent you, okay? Now, you get this pair of systems and you try to decode what element of the group I've sent you. Data processing inequality says you're not going to get more information about the group element I sent you just because these guys have unitarily evolved in a rotationally symmetric manner during the course of that transmission. And so the sum total composite of apparatus and particle has to have no more asymmetry than it did before. And given that the particle now has some asymmetry, that means that it's going to have to be compensated by the apparatus.
All right, thanks.
How many minutes do we have left? Sorry.
You're -5, but...
Oh, -5. Well, we can end there. Or do you want me to say what? Time reversal symmetry?
Yeah.
Read our latest paper. It's all about time reversal symmetry. The paper's called, what's the paper called, Ela?
Whether quantum theory needs complex number, the foil theory perspective.
Perfect. And now you know what a foil theory is. So yes, it's very much, that paper is very much about the difference between time reversal symmetry and other symmetries that we've been talking about today. So that's my answer. Just
I can give you like 2 minutes to...
2 minutes to wrap up. Okay, good. Yeah, what do I want to say? Is there anything I really need to say? Yeah, okay, maybe I'll take 2 minutes to talk a bit about okay. So yeah, maybe I'll say something about this sort of diversity of resource theories. There's asymmetry, athermality, entanglement. How should I think of those different things? I like to think of it this way, that in addition to the revolutions in physics, which sort of overthrow the previous theory, there are revolutions in physics which are kind of more gradual, where you sort of change your perspective on an existing theory. And that often happens by realizing that the existing theory can be well summarized by some set of principles. So like a nice example is that Newton's theory got transformed when it was realized that you could characterize it in terms of least action principles by people like this. And it's not as if we overthrew Newton's theory by virtue of doing that, but that reconceptualization of Newton's theory is what paved the way for theories that came afterwards. Okay, they sort of set the stage for innovating over Newton's theory. And the same is true of symmetry principles, applied by Lagrange, Curie, another, Wigner. Same thing, thermodynamic principles, and I think these days, information theoretic principles. So if I look at historically, how have we thought about information in physics? There's one slogan, which is that information is physical. So this is due to Rolf Landauer. And there the idea is that if you're in the business of building a computer or a cryptographic system, you should take the laws of physics into account, because that's ultimately what determines the fundamental capabilities of what you can do. So that's the point we were talking about before, that pragmatically the laws of physics are sort of relevant to what we can do in the universe. But there's another point of view, which is that physics is informational, which I would characterize as, taking an information theoretic perspective on physical theories can deepen our understanding of them and lead to new and transformative developments, like what we just saw. That this notion of asymmetry, you might have thought it has nothing to do with information theory, and then you realize, oh, well, actually, a measure of asymmetry just is a measure of information. And this is happening all over the place, where I would say, now is the time to reconceptualize all of physics from this information theoretic angle, because it's never been thought of that way before, and we're going to not necessarily immediately overthrow the theory, but we're going to have a new perspective on it, which is going to allow us to make some progress and maybe go beyond quantum theory. So like the examples of like revolutions that were came about in this way, if I look at early quantum theory, it came from thinking about action principles. So this was like de Broglie's work, where he saw the analogy between the principle of least action in optics, which is Fermat's principle, and Maupertuis's principle in mechanics. And he knew that ray optics was an approximation of wave mechanics. And he said, well, look, if this principle of least action holds in both cases, then shouldn't there be something like wave mechanics over here in the matter? sphere. So if we'd never had like least action principles and we didn't have Fermat and Maupertuis principles, he wouldn't have seen that analogy and we might not have had wave mechanics, right? So that it's the principles that were key to thinking that through. And of course, thermodynamic principles applied in Planck and Einstein's work. Symmetry principles were obviously used by Einstein to develop relativity theory. And there's a nice quote by Enrico Fermi that says that prior to Einstein, symmetries were something that you deduced from your physical theories. And post-Einstein, symmetries are what you build into your physical theories at the beginning, right? And that's a big change in how we've been constructing theories. If you look at the history of QED, well, we needed the path integral formulation of quantum theory because canonical quantization didn't work. And that relied on Feynman's generalization of least action principles through the form of path integrals. So again, if we didn't have least action, we couldn't have gotten QED. And the question is, well, where's this information theoretic angle potentially going to lead us to in the future? Yeah, so with that, let me just leave off with this picture and I guess open it up for questions if we have time.
So we're anyway starting now 10 minutes late, so you get still half an hour of coffee break, so you can ask questions.
We should go straight to coffee. Yes.
So in history of physics, as you've shown,
Yes.
so for me, rather like the action principle or the assumption of symmetries is rather like an ontological assumption about the world, and information theory is more like not the theory about the world, but it's more like a theory of how we can do information.
Mm-hmm.
So for me, it's like two different things.
Okay. So if I take Carnot's work, which was about steam engines and how much work I can extract from a steam engine, it's much more like information theory in the sense that it's like plumbing. It's, you know, oh, that's a dull thing. How much work can I get out of a steam engine? Much like how much information can I send down this channel? That's an engineering problem. And yet, steam, you know, the study of steam engines led to thermodynamics, which is a very big part of our explanation of the origin of life and the evolution of stars and the beginning of the universe. So I don't think it's true that just by virtue of it starting in pragmatic roots about what agents can do in this universe, necessarily it is destined to be somehow lesser than the least action principle was, simply because the least action principle could be formulated from a God's eye perspective that doesn't involve agents.
Yeah, maybe, yeah, but I think for me, information theory is still more like some mathematical, closer to math, right? So for me, it's like a tool rather than something you can say about the world. I mean, yeah, but I would agree that we could use some assumption of information theory, then to include how the world is, and then from that to follow like new physics.
Well, let me see if you agree with this, that information theory could be thought of as being about the world. Namely, it's about how agents in the world can learn about other systems external to them. So if I think of every agent as a system in the world, then constraints on what agents can do, like how much work can they extract in a given situation, how much bits of information can they communicate, are still facts about the world. Because anybody in the world, an alien civilization, us 1 million years from now, will be limited by the laws of physics. And so those capabilities will have fundamental limits still.
Yeah, I understand your point.